Hello and welcome back to part two, where we're going to look at some concepts in nuclear chemistry, which is part of the atomic structure unit that we did early on. But just a reminder that when we talk about nuclear chemistry, there are some nuclear particles that we talked about that represent either particles in the nucleus, particles outside the nucleus, particles, that other particles can produce as they decay and break down. And so we're going to first review some of those basic particles and the notations that they have. Alpha particle, remember its symbol. Is helium with a mass number of 4 and an atomic number of 2. So remember, an alpha particle is basically when the nucleus ejects 2 protons and 2 neutrons. You can also write it with the Greek letter. It does technically have a +2 charge, although the charge is often not written with it. A beta particle is another name for an electron. These are typically electrons that are produced from the decay of protons or neutrons in the nucleus and then ejected from the nucleus. So notice the symbol for beta particle, E for electron, mass number 0, and then -1 at the bottom. Or you can use the Greek letter beta. And again, mass number 0, and then -1 where the atomic number would be. A positron is a particle that is again produced from the decay of protons and neutrons in the nucleus. It has the same mass as an electron, but exactly opposite in charge. And so notice the symbol for a beta particle and a positron are very similar, except for the fact that the beta particle has the -1 at the bottom and the positron has the +1. A proton, you will see it either as a hydrogen element symbol with the mass number and atomic number of both 1, or the lowercase p for proton, again, mass number and atomic number. A neutron, there's the symbol, lowercase n, mass number 1, atomic number 0. Gamma rays are electromagnetic radiation, and so gamma radiation is just the Greek letter gamma. You might see it with zeros for the mass number and the atomic number, but these are really high energy photons. They are able to penetrate quite a bit, and so the penetrating ability for these different types of particles that are produced as nuclei decay, right, they do have different energy, and the idea of nuclear shielding is you want something dense enough to block them, and the more energy they have, the more difficult they are going to be to block. But when we talk about radiation and we talk about elements being radioactive, we are talking about the nuclei of those elements ejecting these particles, and it's these particles that are the radiation that we talk about, remember, right? And so one way to represent the decay or other processes is by a chemical equation. In this case, for nuclear equations, remember, nuclear equations differ from normal chemical equations because for nuclear equations, there's not a conservation of mass. There's a very small loss of mass as these between the products and the reactants. What is conserved, in other words, what doesn't change, is the total mass numbers and the total atomic numbers. So if we look at these examples, you'll notice that the atomic number is conserved, and the mass number is conserved where mass number member is the top number, and on the reactant side we have 235 plus 1, which gives us 236. And on the product side, we have 138 plus 96 plus 2 neutrons. So remember, that big number means there's 2 of these particles, which means there's 2 neutrons. And so 138 plus 96 plus 2 also gives us 235 or 236. So you'll notice that the total mass number does not change on both sides of that reaction. The atomic number we'll see also is conserved, does not change. 92 plus 0 gives us 92. And 55 plus 37 plus 0 gives us, again, 92. And so the fact that these two numbers are conserved allows us to predict what's missing in a nuclear equation should something be left off. Because if we know that the mass number and the atomic number are conserved, then we can figure out the missing mass number and the missing atomic number, and then we can figure out what exactly is what the particle is that's missing. Okay, so let's look at some examples where, okay, we have radium-226 and 88, right, and there's a missing particle. So we know that the mass numbers and the atomic numbers have to add up. Well, we have 88 on one side, and we have only 2 on the product side, so we need we need 86 more protons. So 86 plus 2 gives us 88. And we need 222. So 222 plus 4 gives us 226. Now the symbol that goes along with this is the symbol for element number 86. And element number 86 is radon. Here we have iodine, 131, decaying by beta emission. So 0 plus 131, right? 131 plus 0 is going to give us 131. Now remember, beta particle has a -1 down here. So we need something plus -1 is going to equal 51. So remember, that negative number is like subtraction. So 52 plus -1 gives us 51. And element number 52 is tellurium. Now, some different types of decay based on the particles that are produced. Notice that for many of the decay processes, that when you see decay, that alpha particle or beta particle is a product. It's given off. And so for an alpha decay, right, we have one isotope giving off an alpha particle. So there's our alpha particle. And it's producing what's called a daughter isotope. And that daughter isotope is going to be lighter by 2 neutrons and 2 protons. If we have a beta decay, well, we have an isotope, and it's producing a beta particle plus another daughter isotope. And so the result of that beta decay is the mass number is not going to change, but we will see a change in the atomic number. We will see the new isotope have an atomic number 1 greater than the isotope that we started with. Positron emission is, again, emission decay. That particle is given off. And so positron emission, again, we have one isotope, and it's giving off a positron. In that process, the mass number does not change, but the atomic number will go down by 1. Okay. Now, some other types of decay processes. Electron capture. This one's a little bit different because the nuclear particle is being pulled in, right, to the nucleus. And in that process, the isotope, as it pulls that electron in, what ends up happening is the mass number doesn't change, but what does change is that the atomic number will decrease by 1. So a neutron will become a proton. Okay. Now, there might be some X-rays produced. There might be some gamma particles produced for these. Okay. Gamma emission, things that decay by gamma emission produce very high energy gamma rays. They're very, and so that can happen in many different ways. You can have isotope that is excited, right? Higher energy, and it's releasing energy, and it can form gamma rays. Gamma rays are also produced as in a lot of other decay processes, where they are produced as well. But notice gamma rays do not change the mass number or the atomic number. It's a way of releasing a large amount of energy. Things can also decay by spontaneous fission. So fission there are isotopes that undergo spontaneous fission. These are the isotopes that are also used in nuclear power plants and nuclear weapons, like uranium-235 and plutonium isotopes, where you have a parent isotope, right, like uranium-235, and it splits into smaller isotopes and produces some neutrons. Now, often this has to get started by using a neutron, but as we look at kind of fission and fusion, we'll see that fission, you have a larger isotope breaking up into many smaller isotopes called daughter isotopes. And so a lot of times there is a neutron that has to get started, and then that allows the fission to progress, and you get your daughter isotopes that are smaller, right? So fission is things breaking apart. And more neutrons are produced that can also produce more fission reactions. And so in a nuclear power plant, we make use of those, right, to produce energy. In nuclear weapons, we make use of that and allow it to go uncontrolled and make big explosions. Fusion is the opposite. Fusion is when you take smaller isotopes and they come together to make something larger. And so fusion, smaller coming together to make something larger. So in this case, we have these two lighter isotopes of hydrogen, deuterium and tritium, coming together, and they attract each other. They release a neutron plus an isotope of helium. So notice helium is larger than either of the isotopes. It has more protons and more neutrons in its nucleus than either of the isotopes it started with. So we have smaller things coming together to form something larger. And again, right, both of these release quite a bit of energy because a little bit of the mass isn't accounted for, and that mass gets converted to energy, and that energy is released. And when you have billions upon billions upon billions of those atoms undergoing these processes, that's a lot of energy. The speed or the rate at which something decays is given by the half-life. And so remember, the half-life is the amount of time necessary for 1/2 the nuclei in a sample to decay to a stable isotope. Now, they don't always decay to a stable isotope. Sometimes, they decay to something that is more stable but still radioactive. So kind of keep that in mind. Where, if we take a look at the half-life of something like uranium-238, it will decay eventually into lead. It has a half-life of about 1 billion years. And so after one half-life, half of the uranium is left and half has decayed. After a second half-life, half of the uranium is left, right? So we have half of a half is left, or a fourth. And then after 3 half-lives, we have half of a half left, or an eighth is left over. And so on until we have, in essence, none of the original isotope left over. And so it is a mathematical relationship. Right? It is not a linear function, and we'll look at it in more detail. But review your other notes and you'll have lab to do virtual lab to do and an assessment, so make sure you're watching these as you first before trying anything.